Welcome to my science project. I'm Daniel DeHoorty, and this is Light Waves in Space Exploration. Here you see a normal, average star, medium-sized and yellow, kind of like our sun. It's being detected in visible light rather than infrared. But then, when we turn on our infrared detector, here's what happens. Boom! Now, it's being detected in its infrared form. This allows us to see stars through thick gases and from far away, multiple light years. Some of our most powerful telescopes can detect stars in infrared, almost like our Hubble. Infrared uses heat as some of its visible light. Besides all of the space telescopes that the world's various space agencies have to detect infrared wavelengths, there are also a various number of telescopes on Earth that can do the same. For one, there's VISTA here in northern Chile, the most powerful on-Earth infrared telescope. Then, over here, all the way in Mauna Kea, Hawaii, is Euclid, the second most powerful on-Earth infrared telescope. Then over here in Wyoming, there's WIRO, an infrared on-Earth telescope completely and totally operated by the University of Wyoming, and it is their crowning achievement. So, let's say you're in a car, sitting, waiting to get to your ride to school or whatever else. And then a fire truck comes by. At first, it's not too loud and definitely not too high-pitched. But then as it gets closer to the car, the wavelength of the sound increases. Then, as it gets farther away, it decreases again and becomes softer and less high-pitched. You can understand why the loudness increases and the pitch increases too, thanks to the wavelength. This is all because of the Doppler effect. But what does this Doppler effect thing have to do with space exploration, you might be asking? Well, I'll show you. Here we have our old star again, except it has a planet orbiting it this time. Now, let's watch the planet quickly orbit around the star. Did you catch it? That wobbling that the star had as it was attracted to the planet's gravity? You might not have, so I'll go through it in slow motion. As you can see, it goes around the star, and the star is attracted to its gravity, so the star wobbles in correlation with the planet's movement. You still don't know what that has to do with the Doppler effect, though. Well, the Doppler effect isn't just for sound waves. It's for all waves, whether light, sound, radio, any kind of wave. All the Doppler effect applies to every kind of wave. So, as the star wobbles, it gets slightly closer and farther away from Earth. And see, just like that fire truck, as the star moves farther, it becomes farther away and the wavelengths get longer, making the star appear redder because the longer the wavelength, the redder. And as the star wobbles closer to Earth, it gets slightly bluer. The shorter the wavelength, the bluer the light. This can't be picked up by the human eye, which is why you don't see stars as like a time-lapse of their orbit wildly flashing a rainbow of colors. It can't be picked up by the human eye. It has to be picked up by special, trained by thousands of scientists, telescopes like our Hubble and the telescopes that you were shown earlier that are on Earth. The Doppler effect causes these slight changes in color, and depending on how much the star wobbles, that's how much the color changes. And depending on what the planet is like, that's how much the star wobbles. So by the color change of stars light years away, scientists can tell about the planets around it. This is our main method of discovering exoplanets, planets outside the solar system, besides the infrared vision we talked about earlier. Another way that scientists use planets and stars and their movement to figure out where they are and what they're like is when a planet's orbit is directly in between the star and Earth, like so. This causes, because of the planet blocking some of the light, for the star to dim. And depending on how much the star dims, we know what the planet is like.